All right. Hello, everyone. It's a lot of people. Thanks for coming. Yeah, so hi, I'm Nico. I'm a tech principal at Ableton. We're a company here in Berlin. We make software and hardware for music production. I also like music, as you can see. I'm playing the guitar. And yeah, when I'm not playing music, I also like playing video games, old and new ones. And I like to collect vintage computers, so like this one here, which are great for playing old video games. And as it turns out, video games are also a good topic for my motivation. Because if you think about video games, they are basically state machines all the way down, right? So let's imagine you have some kind of video game and you start the game, and then you're in the main menu, and you can go to the start a new game, you get a loading screen, you go in-game, and at this highest level, it's a cycle, and it repeats basically. So this is your global game state. Then while you're in the game, you might also have states as part of your game, like you're just playing the game, or maybe there's a cutscene playing to tell the story or something, or maybe you have some kind of menu where you can do crafting or whatever you do in games these days. And then as part of the gameplay, obviously, you will have enemies, characters, all kinds of things that will also have some kind of state, like an enemy might be waiting for the player, approaching the player, looking for cover, these kinds of things. So lots of state machines. And yeah, you need to somehow model this in your code in order to implement all this functionality. And to make it a bit more concrete, I prepared a small example minigame. See if this works. Yeah, right. So yeah, it's a small space battle game. You have these two spaceships fighting each other. And so the one now in the center is my enemy. And as long as I'm on the outside, he's going to just stay in the center and from time to time fly out, do a little loop. But if I go in the center, then he's just going to circle around me like this, keep shooting at me. And on the right, you can see a visualization of the state machine of this, the, in air quotes, AI of this spaceship. Yeah. So, and that's the state machine, basically, for the spaceship. So it can be circling around me, it can be in the center, and shooting at me from the center, and then you have these in-between states where you transition from being in the outside and flying in, or being inside, flying back out. And okay, so now you want to program this game, and you need to represent this state machine in your code. One way you could do it is the more traditional, almost C-like way. So you have an enum to represent the states of your state machine, and then in addition, yeah, so up here you have your enum, and then in addition you have all these variables that you need to implement the behavior. For example, you want to know how much time has passed since the last time you fired a shot in order to control how rapidly you fire. When you're in the center and you want to do periodically these loops back out, you need to keep track of how long you've been in the center. And then also, when circling around, it's actually 4 positions that you keep flying along, and so you need to know which position next to fly to, basically. All right. So, and then each frame, you do a switch on your current state, and you do whatever you need to do based on the current state. And that's all fine and working well. But there's one problem with this approach. So we have these 4 states, and we have these 3 additional variables. And these variables are only relevant for certain states. So if you look at the time since the last time we fired a shot, it's only relevant when I'm shooting, which is the case for the circling state and the shooting from center state. The time that I spent in the center is only relevant when I'm in the center. And the position that I want to fly to next is only relevant when I'm currently circling. But if we write our code this way, then there's not really a correlation between the states and these variables. And now this is a pretty simple example, so it's pretty easy to get it right. But you can imagine if it's much more complex, then you could easily get into situations where you accidentally use the wrong variable in the wrong state, or maybe you forget to reset something to the right value when switching between states, and so you can easily get bugs, and the compiler doesn't really help you avoiding these bugs. So can we do better? Is there some way how we can model the state machine in our code in a way that these impossible states are impossible to represent? And one way we could do it is by having objects represent our states. So like the circling state would be an object, and it would have all the variables that are relevant for the state, and then same for shooting from center, and then for these other ones. And then we need some way to refer to these objects as like a generic state thing. And there are different ways you can do something like this. You could go the OOP route and make a big class hierarchy and all this kind of stuff, but that's maybe way too complicated for this thing. As it turns out, if we look into type theory and functional languages, then there's a thing that's perfect for what we want to do. It's called a sum type. So what is a sum type? It's a data type which can be one of several types, and it can only be one at one time. So this is a bit abstract maybe, but basically you can have an object that can represent different types, but only one of them at one time. And so how could we do something like this in C++? Already in C we have a union, which is kind of like this. So you declare a union, and it has these different types, like int and float. And it can represent any of them. But the problem is that you need to manually keep track of which one is currently active. So you need something like an additional tag, it's sometimes called, to then make it a tagged union. And then you can wrap it up in this way, and you have a tag and a value. And then you can switch on the tag, and then you can do the right thing for the right value. But you need to manually keep this in sync. So if you change whatever is in the union, you also have to change the tag. And also unions don't really work very well with anything that's not a trivial type, anything that requires construction, destruction. It's possible as of C++ 11. It wasn't before possible at all. But you basically have to manually write constructors and destructors, and you have to do placement new and call destructors manually and all kinds of stuff. That's not very pleasant. So that's where SD variant comes in C++ 17. It's basically solving these problems for us. It allows us to declare a type, like here I call it value, that's a variant of all these other types, in this case int, float, and string. And it keeps track of which one is currently in there. And it also makes sure that it's type safe. So if you put an int in and try to get it out as a float, this won't compile. Whereas with a union, that's not the case. And so you can declare your variant, and then you can construct instances of it using either of the types that it can represent. You can, once you constructed one, you can change its type by assigning something else. You can even put them in a vector because it has value semantics. So yeah, you can have a heterogeneous container if that's what you want. And then the question is, okay, so now I have my values in this variant. How do I get them back out? Since it's type safe, it prevents you from interpreting one type as the other. And there's a couple approaches for this. So on one hand, you have this API with a function called holds alternative. And it basically tells you, okay, am I currently holding an int or whatever type you want? And then there's a get function, which also takes the type that you want to get out. And if it doesn't actually have an int here, then it will throw an exception. And so then you can do this if-else-if chain and test every possible case and get the things back out. And then there's a different API, which is getIf, which is pretty much exactly the same, but syntactically a bit different. So it doesn't throw, but instead you say getIf, and it returns a pointer to the object in the variant if the type matches, otherwise returns a null pointer. So yeah, exactly the same thing, basically. And if you have a simple case where you maybe have 2, 3 types or whatever in your variant, works pretty well. But there are 2 problems with it. On one hand, it's kind of cumbersome to write these if-else-if chains, these long chains of all these cases like this. And also, it doesn't tell you if you forgot one of the cases. So it's called exhaustiveness check. And basically, if you have this variant and later on, and then you have 10 places in your code where you look at what's inside, and then you add another case, the compiler will happily compile it, and you will forget to handle it. And so then, this is what solves these problems, the visit function. And how it works is you call visit on your variant, and you pass in a visitor object like this, which has operator call overloads for all the types you want to handle. And if it doesn't provide all the overloads, it will give you a compiler error. And also, the problem is with this that it's kind of clunky. You have to write this separate visitor class, and as soon as you want to, in here, refer to anything that's in the scope of where you're doing this call, then you have to pass it into, have members in this class and pass it in on construction and all this kind of stuff. So yeah, that's quite clunky and not so nice. So let's see if pattern matching can help us with this. So what's pattern matching? I found this definition on actually the website of the Scala language, but I think it's a good definition. Pattern matching is a mechanism for checking a value against a pattern. Okay, well, yeah, duh. But a successful match can also deconstruct a value into its constituent parts, and we'll see what this means. In general, it's a more powerful version of the switch statement and can be used in place of a series of if-else-if statements. And so the general idea is for values, you can match values, pattern match values, and then you would maybe have something like this, where you have some value and you want to handle different cases of this value, like if it's exactly 5, I want to do one thing. If it's between 6 and 10, I want to do another thing. If it's not negative, I want to do, no, if it is negative, I want to do something else, and so on. And with pattern matching, instead of writing this out manually, this if-else-if chain, you would do something like this. So this is pseudocode. This is not C++, unfortunately, but it is relatively similar to constructs in languages that support it. And so it's a much more structured approach on one hand. So instead of having this if-else-if, and which is a bit more verbose, and you have to basically find the relevant parts between all the syntactic noise, it's a very clear, almost table-like thing, where you see your patterns on the left, and then what you want to do based on when this case happens on the right. And you have often have a lot of syntactic sugar, like you might be able to specify a range in this way, or you might say, okay, I want to match any value that satisfies this condition. And then you might often have something like a placeholder, where you can say, okay, anything that doesn't match any of the previous patterns, I want to handle in this case. And then, so this is a very common thing in functional languages especially, and some other modern multi-paradigm languages also have it. So let's look at how this looks like in a functional language. So this is not Haskell, this is still C++, but this is like the textbook's example for a factorial function. If you would learn about recursion, then you might have come across something like this. If you write it in C++, then you would write a function, and you would first check, is my value 0? If that's the case, return 1. Otherwise, return my current value times the factorial of the value minus 1. And then recursion does its thing, and you get the right value. And in Haskell, you would write it like this. So you'd explicitly list out these two cases. And you would write, okay, factorial of 0 is 1, and factorial of n is this expression. And so already the way you define functions in Haskell is based on pattern matching, because you can have these different cases and you can specify various expressions for when this case should be used. And so we just saw std variant, which is a sum type. And pattern matching also goes along very nicely with sum types, because you can basically do a match on the type that's currently in the sum type. And then based on the matching type, you do certain things. And let's again look at a Haskell example. So this is how you would define a binary tree, or one way how you can define a binary tree in Haskell. A tree is basically a sum type that's either a leaf node or a non-leaf node, which then has two trees as children, so which are then recursively again a tree. And if you want to write some function to do something with this tree, you could use pattern matching and say, okay, if this tree is a leaf node, then I do something. If it's not a leaf node, I do something else. And this is where we also get this destructuring, because so a non-leaf node has these two children, and here we say, okay, I want to pattern match the case that it's a non-leaf node, and I want to give the names left and right to the two children of the tree node. And then I can refer to them inside my function. Another example from another language, Rust. And yeah, there you can define this enum thing, which is also a sum type in this case. And you have these different cases, and some of them have some data members. And then you can do pattern matching on an instance of this message and do different things based on what type you have. And you can also assign new names to these members and do all these sorts of things. Yeah, so this is pretty useful. Wouldn't it be cool if we could do something like this for a C++ variant? And we can't, unfortunately, not yet at least. But for the special case of std variant, we can do something that's relatively close. So if you go on the CPP reference page for std visit, for the function that you can use to apply a visitor to a variant, you will actually find this code over here, although condensed down to 2 lines in one of the examples. And this is, yeah, I don't want to go too much into how it works. I'm happy to explain it afterwards, but it's actually quite funny how it works. But basically, you can take this magic piece of code and put it in a header file somewhere. And then instead of having to define this visitor separately from where you want to visit, you can just create it on the fly based on lambdas. And you just write overloaded and then put in your lambdas, and then you still get a compiler error if you don't handle all the cases. And also, if you want to have a generic like placeholder thing that matches everything, you can put in a generic lambda with autoref or something, and then it will match everything that's not covered by the other ones. And so then, once we have this, there's still one thing which I don't like, which is that you have to, on one hand, you have to put this overloaded, which is a bit of additional syntactic noise, and you have to specify the variant last and the visitor first, which is a bit backwards from the way I would like it to be. I would like to be able to say something more like this, where I say match this variant and then all the cases. And so, but once you have this, you can pretty easily write a match function where you take the variant first and then all the different lambdas, handler functions, as a variadic template arguments. And then you internally use this overloaded helper and just forward the lambdas and also forward the variant. And so, yeah, it's another magic piece of code you can put in your header file. And then once you have this, you can write code like this, which is not too far away from this, actually. And so, yeah, of course, this is not real pattern matching. C++ doesn't have it as a language feature. And you can't do, for example, destructuring. You can't use it for values or anything like this. But I personally think it's already very helpful. And as we'll see in a moment also, there are already quite a few use cases where you can benefit from this. But first, so this is C++ 17. Both std variant itself, as well as the way you write this overloaded thing. What if you still on C++ 11 or 14? What can you do then? And fortunately, you can get pretty much the same result because it's all library code in the end. And so if you want a variant, you actually have tons of options. There are many libraries that provide it. Boost has one if you want to use that, although I think it even works in C++ 98, so it requires a lot of preprocessor stuff, and so it's pretty slow to compile. It's also a bit different from the version that's in the standard. Sorry. Then there are these other ones that are, this one, for example, requires C++ 11, but then also builds faster and is more lightweight. It's a bit closer to the standard as well. Then there's this one from Michael Park, Park variant, which is actually based on the implementation that's in Clang's libc++. And yeah, there are other libraries that provide a variant implementation that's very similar to the standard one. So you can basically use it, and then once you upgrade your code base to C++ 17, you can search and replace all of them with std variant. And so once you have a variant, you still need this overloaded magic thing in order to write your match function. And I found this variant implementation, mapbox variant, which actually includes an implementation of, they call it make visitor, I think. Yeah, make visitor. That's more or less equivalent to this overloaded thing I showed. And it's in one header as part of this project. And you could basically just grab it from there and stick it in your project as well. And then you can write this match function based on this. And so even though it's part of this library, it actually works with pretty much any variant implementation that has the same interface as the standard one. And here's a Godbolt link for applying this visitor to the standard variant, if you want to try it. All right. So my motivation in the beginning was state machines for games, but I want to show a few different examples. So I want to go a bit more in detail in the state machines, how you would implement it using this pattern. But then I also want to talk about event handling, which is another use case where this pattern can be applied. And then I'm going to show a few more examples more quickly, just basically, okay, there's other stuff you can do. All right, so let's get back to the state machine. And let's recall this was our state machine with these 4 states. We can be circling around, being in the center, and then can fly from the outside to the inside and from the inside back out. And if we want to use this pattern, we would represent all of these states as structs. So we'd have one for the circling state, and it has just the variables that are relevant for this state. Then we have this fly to center type, which is an empty type. It's just to indicate the state. The state when we are in the center would then have this time spent in center. That's only relevant for this state. And then the fly out is a little bit of an implementation detail, but it actually has the index of which corner you want to fly to after you've reached the outside. But yeah, then we can define our state as a variant of all these types. And then each frame, when we want to update the behavior of our spaceship, we can do this pseudo pattern matching on the type that's currently in the variant. And then we can write code that's like this, where we say, okay, match on our current state. And if we are circling, then we do whatever we need to do. If we are flying into the center, we check if we have already reached the center. If that's the case, we go into this state, and so on and so forth. And since you have all the variables that are important or relevant for a certain state as part of the type representing the state, you make it impossible to represent these invalid states, basically. And also, when you transition from one state to the other, just by creating this object, you invoke its constructor, and you make sure that the values are set to the right values that you need to have when you enter the state, which is also pretty nice, less to think about. Okay, so there's one pitfall with this approach that I ran into when I started using this, which is state transitions. And so the naive way how you might implement a state transition in this pattern is, okay, so you do this pattern matching and you see, okay, I'm currently in the flight to center state. And in the flight to center state, what I do is I check, have I reached the center? And if that's the case, I want to go into the being in the center state. And so you could do it like this. So you could capture so this is some code inside a method of the spaceship class. And you can capture the disk pointer, and then you can just assign to the mState member variable the new state. And in this case, it will work fine. But what if you have codelets like this, where after you've reassigned the state, you want to refer again to the reference that's your function argument. And the problem here is that this state is a reference to an object that's inside the mState variant. And as soon as you reassign a new object, it gets destroyed. So after this line, state is a dangling reference, basically, and which means you get undefined behavior if you then try to refer to it. And now you might say, okay, well, this is such a small code example, I would immediately see this. Why do you think there's a problem? But in practice, maybe this line where you assign mState to something new might be a function that does some more things. And at least in my experience, it's actually quite easy to accidentally do some change your current state and then still not exit from your current function or your current lambda and still refer to the state. And so in order to avoid that, what I've settled on is to define an optional of my state type, so of my variant. And by the way, optional is also a sum type. It's a type that represents either a value or no value. And it's handled pretty much the same way in languages that support this natively. So I define an optional new state, and then I say, okay, my match function, or rather the lambdas that I pass to my match function, need to return an optional new state. So if they want to transition to a new state, they have to return the new state object. If they want to stay in the same state, they return an empty optional. And then I can check, okay, did I get a new state? If that's the case, then I assign. And then my function would look like this. If I reach the current target, I return the new state. Otherwise, I return an empty optional. And this way, I can sidestep this issue and make sure I don't make any mistakes. All right, so let's evaluate this, the application of this variant pattern matching to this use case. And in C++, we always like to talk about zero-cost abstractions. So let's see what the cost is of this. Is this a zero-cost abstraction? Well, not quite, unfortunately. So I compared this implementation that I just showed using the variant pattern matching and the one I showed in the beginning, where you just have an enum with the states and then all your variables just as members. And so I looked at compile time by just compiling the translation units that are affected by how you implement this sequentially, so no parallelization or anything from scratch. I looked at the binary size, and I did a micro benchmark of calling this update function that then does a match on your current state. And what I found was that compile time goes up by, on this machine, roughly 200 milliseconds, which is, you might say, okay, that's maybe not too much, but you think about it, if you use this pattern 10 times in your code, then your compile time goes up by 2 seconds already. So yeah, I guess needs to be evaluated case by case. Binary size, so this is a release build, but still there are debugs or there are symbols in your file unless you strip it. So if you don't strip it, binary size actually goes up by over 1 kilobyte, which seems quite excessive. But in this particular case, if I strip symbols from the binary, it actually comes out to the same, fortunately. And then regarding performance, so we go from 6 nanoseconds per iteration to 9. So we need 3 nanoseconds more. Again, I guess it depends really on your use case. If you're doing high-frequency trading software, then you probably care about differences like this. But there are probably many cases also where, yeah, what are 3 nanoseconds? So yeah, depends on the case. But as we can see, it's unfortunately not zero cost. There's a measurable cost here. But regardless of this, I think it's a good pattern. It guarantees your invariance. You make sure that invalid states are not representable. You get this exhaustiveness checking also, so you make sure to handle all the cases in all places, or explicitly say, I want to have a placeholder, I want to only care about one certain state. And it's a pretty straightforward translation from the conceptual model of your state machine, of how your thing works, to code. On the con side, it's a bit, well, dangerous, maybe. You basically need to be aware of this state transition pitfall, and you need to make sure that you do something to prevent this. And also, there's no formalized separation between what you do for each state and the state transitions. So if you think about state machines as the formal concept, then it's actually pretty well defined. Like, you have states, and then you have events that trigger transitions between these states. And I think if you have a small state machine with like 4 or 5, maybe 6, 8 states, this is a good approach. But if you have something really complicated with lots of states and also many ways how you can transition between them, then you might want to have a more formal approach and maybe use some kind of state machine library where you are able to declare, okay, these are my states, these are my transitions, and so on. So yeah, depends on your use case. So overall, I personally like this pattern a lot. I think it's a very straightforward way to represent state machines. And there's, as it turns out, in my experience at least, there's a lot of stuff that you can represent as a state machine in your code, and where your code becomes easier to think about if you explicitly model your state machine instead of implicitly encoding it in various flags or whatever. And so if your logic can be organized as a state machine and the number of states and transitions isn't too large, then I would say, yeah, use this pattern. It's a good one for this case. All right. Now, event handling. Event handling, I think, is another very good use case for this pattern. And so, why is that? So let's imagine you write some desktop GUI application and you want to handle mouse clicks and keyboard events and all this kind of stuff. And so if you think about it, these events are all, on one hand, they tell you what event occurred, like, okay, the mouse was clicked or a key was pressed, but then you also have associated information with each event. Like for mouse click, you would know, okay, at which position and which button was pressed. For a key press, you would get the key code and whether it's a repeat event because the user is holding down the key, something like this. And then you might have other events like your window has been resized, and here's your new width and height for your window. And so again, you can represent this, these different events as different types and then have a sum type that represents a general event. And this way you can make sure that you have the right information only as part of the types that represent specific events. And so this is operating system interaction, but you can also use event handling internally in your application. So maybe if you're writing, some kind of server, maybe you have events like a client connected, a connection got interrupted, things like this. And here maybe you also have some information specific to certain events that you want to represent. So back to the operating system interaction, how is this typically done? And from the libraries and frameworks that I looked at, I could see mainly 2 approaches, plus the Windows API, but let's not talk about this one maybe. So X11, for example, and all the Unix user interface server thing, and also a bunch of platform abstraction libraries like SDL or SFML use a tagged union. So they basically have a union of structs that representing each event, and then an additional enum indicating which event you actually got. which suffers from type safety, because you need to make sure that, okay, if this is a mouse click event, I need to access the mouse click member of the union. And if I accidentally access the key press member instead, then, well, that's my fault. The other approach, which you have in Qt, also GTK and Coco, maybe other ones, is that you explicitly have one handler function for each type of event, which then gives you type safety because only the button press or the button press function would only take a button press event, and the mouse or the keyboard press function would only take a key press event. But I think it leads to more boilerplate. In some cases, you need to inherit from some kind of class in order to be able to handle events. In other cases, you need to explicitly hook up some kind of callback to a specific event. So, at least personally, I think I prefer this approach, where you can have a single function and then dispatch to all the different cases of events, but type safety. And so I made a small example again in this case, where I implemented event handling using this pattern matching approach. Let me show it. Okay, so this is my very exciting window. And if let me also make this not smaller, but bigger. Okay, that's maybe enough. Right, and so if I move my mouse in here, it tells me my mouse was moved. If I right-click, it tells me that the right mouse button went down and up again, and also that it's not printing mouse moves anymore, so now I can move freely without getting all these prints. I can press the left mouse button and hold it, and then let go again. And yeah, if I do right-click again, I get these mouse moves again. Awesome. Best application. And how does this look in code? So I have an enum first to indicate which mouse button. And then I have these types for all these different types of event. So I have a mouse moved struct, which has the X and Y position. I have a mouse button down, mouse button up, which each contain the type of button that was pressed, and a window resized event, which I didn't show, but yeah, it also prints that. And then again, you can declare an event as the variant of all these types. And then you can write a pattern matching on this event variant. And you can say, okay, if it's a mouse moved event, then I will check, should I print mouse moves currently? If yes, I do so. If not, I don't do anything. If it's a mouse button down event, I first print that the mouse button was pressed. And then I check, was it the right mouse button? If yes, I toggle between should I print mouse moves or not. And then also print that I toggled. And then it goes on like this. If it's mouse button up, I just print it. If it's window resized, I just print it. And if we compare, if we compare this to the code you would need to write if you use, for example, the SFML library, which uses this tagged union approach. So on the left is the pattern matching approach, on the right is tagged union. You can see that this is quite a bit more verbose on one hand. It's more syntactic noise. You have all these case and break and curly braces everywhere. Whereas the thing on the left looks much cleaner. But also, as I mentioned, you are responsible for making sure that, okay, if this is a mouse button press event, then I need to access event.mouseButton. If it's a mouse moved event, I need to access event.mouseMove. And if you make a mistake there, you get undefined behavior, and you most probably just read some garbage values and you think your mouse moved to int max or something like this. All right. Let's also evaluate this in terms of cost. And in terms of compile time, it's exactly the same as the other one. So, so here I'm comparing the pattern matching approach that I just showed and the tagged union approach. And so yeah, compile time is almost the same. Binary size goes up by 2 kilobytes, almost. And then if you strip symbols, then actually it goes down to 380 bytes roughly, which is maybe not as bad. And here the difference in performance is much less. And I think that's mainly because the cost of doing cout is much higher. So it offsets whatever overhead you had from doing this dispatching and pattern matching. Whereas in the state machine example, I'm not doing a whole lot of work for each case, so the effect is more pronounced. And yeah, so it's 1 nanosecond more that you need. Again, depends on your use case, but probably in most cases you don't really care about 1 nanosecond. So if you do, let's say, 1 million of these, then you have a difference of 1 millisecond, which maybe you care about. Yeah, but depends. But you do get type safety, exhaustiveness checking, and conciseness. It's pretty, not so much code, pretty easy to see. And yeah, I think that's definitely good. If you actually would want to use this approach with an existing platform abstraction library or existing operating system interaction library, then you would have to write an adaptation layer, which translates from whatever you get from the library to this representation. So I guess in that case, it's probably not really worth it. It's definitely nicer, but you probably don't want to sit there for a whole day and just write all this yet another version of all the event types that you already have. But if you're maybe building your own platform abstraction library, then maybe this is a good approach to consider. And also, I think where it really shines is if you do application internal event handling. This is also something we actually do in our code base in certain cases, where we have some internal events for things like a hard drive was plugged in, and now we want to list files that are on this hard drive. And they are represented as types and as a variant of these different events that can occur. Okay, so now we looked at state machines and event handling in more detail. Here's some more examples where I think this pattern can be very useful, but I'm not going to go too much into detail on them. But if you have, for example, a function that can return different things depending on circumstances, it can be useful. And one case where this could be the case is if you have an intersection test between array or a line and a plane, which you might do if you want to write a ray tracer or something like this. So there are actually 3 possible results. You can have the plane and the ray intersecting at a single point. You can have no intersection, or the line can be exactly on the same plane as the plane, in which case it has infinite intersection points. And so you could represent this some way with additional Boolean out parameters or something like this. But if you use a variant, then you can directly encode these different possible results in your code. And you can make sure that you distinguish properly between them. Another example, so this I tried applying this to an opcode dispatcher for scripting language. And you can actually see that on my GitHub repo if you're interested. I don't think that's something you would actually do in practice because performance, and also because it prevents you from directly operating on the binary representation of your opcodes. But it's an interesting thought experiment because there also you have the situation where you have different opcodes, like a jump, for example, would require the address it should jump to, whereas a multiplication or something like this would need some way to reference the values. And so once again, you could have this pattern where you have different things, and the different things have different information associated with them. So yeah, interesting. And yeah, I'm sure there are more use cases where it works nicely. So basically, any time where you have this pattern of I have certain cases that I want to handle, and for each case I need certain data. That might be a good approach to consider. Now, for the end of my talk, let's take a look into the future. So basically, today, this is all we can do in C++, more or less. We can use it with std variant, but we can't do this generalized pattern matching on values. And for example, if we wanted to, I mentioned optional is also a sum type. If we wanted to pattern match on optional, we wouldn't need to write another helper function to be able to do that and stuff like this. That's what we have today, but people are already looking into writing generalized pattern matching libraries. There's, for example, this one, again from Michael Park, where you can say match and then you specify patterns. And yeah, this is how you might implement FizzBuzz using this approach. And I think Bjarne himself also worked on some pattern matching library. And then, even more exciting, there are also 2 proposals currently going on about adding native pattern matching and a native variant to C++ as language features. And just a brief look in some before-after comparison. So this is from the native pattern matching proposal. And as you can see, this is for matching values of an enum. And instead of having a switch case, you can just use this inspect thing, which can be both a statement or an expression. So you can use it to take some action, but you can also use it to produce a value. And then, yeah, you list out all these cases and what you want to have for each of them. And then they go quite a bit further and also do this destructuring thing. And this is how you might even match on the member variables of a struct. So we have the struct player, which has a name, hit points, and lives. And then you match, and you use the structured binding syntax to specifically look at certain members, like, okay, hit points and lives should have these values, and then I don't care about the name, and then I do something. And you can see there's also, you can have additional conditions and stuff like this. So yeah, pretty interesting. And the native language feature variant currently looks like this, almost like a union, except that you don't say union, you say L variant. And then you could put the type and then an identifier for this particular type in your sum type. And yeah, it's certainly much shorter than writing all these structs out like this. And of course, this also then would go hand in hand with the pattern matching proposal, so that you would be able to do pattern matching on instances of these variants. So, right. As of today, pattern matching in C++ is quite limited, but I think it's already useful. There are use cases where you can really benefit from basically faking pattern matching. There is some impact on compile time, binary size, and performance, so you need to evaluate this for your use case. And also one thing which I didn't mention so far. So I said you get an error message if you forget to handle all the cases in a variant, but the error message you get is actually a pretty long template metaprogramming type kind of thing. So if you're familiar with that kind of programming, it's pretty easy to use, but it's much harder for non-experts who are maybe don't have so much experience yet with this kind of stuff. Yeah, and so the hope would be that if these become native language features, that this becomes much easier. You would get better error messages, better performance, compile time, runtime. And yeah, you would have all these more powerful features like destructuring and matching values and all this kind of stuff. So I'm hopeful it makes it to, well, probably not C++ 20, but maybe 23, we'll see. All right, that's it. You can find all the example code that I showed and the slides on my GitHub, which is over there. And I also just want to mention that we are currently hiring at Ableton. So if you're interested in working on music hardware or software, then you can go either to the Meeting C++ jobs website or to our website and look for Software Engineer Live there. Or you can also talk to any of us if you find us. We all have these special lanyards with Ableton logo, so that way you might find us. And yeah, that's it. Thanks. questions?
So is there a good way to do non-exhaustive matching and maybe even force having a default case if it's possible?
Can you say that again?
So currently you need to be exhaustive when you match,
Yeah,
right?
Right.
But maybe you don't want to handle, for example, all events all the time, so you might want to have non-exhaustive matching.
Yeah.
And also, if you develop your library yourself, you want to publish these events, you want to force people, if it's possible, to handle the default case always.
So the latter one, I'm not sure you can do, but you can, if you don't want to be exhaustive, you can always put in a generic lambda, like just put an empty lambda with auto-ref, and then everything that you don't handle explicitly will go into this case.
But then you're forced to use C++14, right? Or is
That is true.
Okay.
That is true, yeah.
Okay.
I was just wondering, in these languages that support this generalized pattern matching that you mentioned before, what is the behavior in case when the cases that we're handling overlap? So for example, you showed an example where we were pattern matching based on an n value of n. So for example, somebody writes if n is between 0 and 5, and there's another case, for example, n equals 4. So what does happen then? Is there like a throw or runtime error or compile time error? How is that handled?
That's actually a very good question. I don't really know. I think there are probably some rules about it, like either it will complain if it's not, what's the word? Not unique, but eindeutig.
Non-aliasing or no
yeah, if you can't figure it out. Or maybe there's some rule about the priority of these, but I actually don't know. Sorry.
Okay, thank you.
Hello, so I have a question about the state machine. So in the example you showed, you had two states, which was circling and shooting from the center, which had a bit of data that was shared between them. So both of them had, I think, a number which was the time since
last shot.
Yeah, that's it.
Let me maybe go to this slide also.
So I was wondering, in that case, would you recommend to create another state, maybe a shooting state, and then have both of those states inherit from this shooting state, so that the member is shared in another struct? And if you recommend that, is it possible with pattern matching to match all the states that are shooting states?
So I mean, what I did in my code is actually, so I don't use inheritance. I just have the same member in both of the structs, but then I have a template function which works on everything that has this member.
Okay.
So that's the way I did. If I understand the second part of your question correctly, it's basically if you have a class and certain states inherit from this class, would you be able to just match this superclass?
Yes.
Is that right?
That's it.
I unfortunately don't think so. Depends on the arcane rules of overload resolution. But yeah, I would need to look into it more, but probably not.
Okay, thank you.
Hi, I was wondering about the performance impact. Do you have any idea what might cause that overhead? And the other question, have you tried measuring one of the C++11 or 14 variants and comparing the performance of those?
So I didn't do that. It's a good idea. I should maybe do that. As for the first question, so I didn't spend tons of time with this, but I did look at the disassembly. And what I could see is, at least, so I only looked into the libc++ implementation. It might be different in different standard libraries. But what I could see is that if you use the variant visit pattern matching style, it creates a table of function pointers and actually creates a function for each case. And then it uses a call instruction. Whereas if you use a switch statement, everything is inlined and you have labels in your code and
That
directly
was
jumps
what
to
I
the
was
stable.
trying to get it with a question because of C++ 11 or 14 lambdas, because I think the standard guarantees that visit is 01. Is that correct?
Interesting.
And that's why it has to do that function pointer indirection. And I thought one of the other might not do that, and that might prevent the inlining.
Yeah, that's possible, yeah.
Yeah. Roughly the same issue. Why did you recommend not to have too many states?
Just because, so basically, if we look at the code, sorry, 1 second. State machines. Yeah, so if we look at the code that you need to write, you basically don't really have a distinction between, okay, this is the logic I'm executing for this particular state, and this is where I transition to another state. So you need to write something like this, where you say, okay, I'm handling the flight to center state, and then if something, and I might do other things in here, right? So it's not in this example, but you might maybe, I don't know, maybe there's a special animation that you show while you're flying to center or something, so you would maybe have some additional code here to do that. And then you also do the state transition. And my assumption is that if you have a very complex state machine with much, that's not like a simple circle, but much more complicated with many states, and they can transition in various ways across, that this might become a bit, yeah, basically this approach then doesn't scale so well anymore. It's just my assumption. I haven't yet tried to implement a very large state machine with this, so maybe it's actually fine.
Okay, maybe, yeah, you should note that you can also use a generic lambda, and then compile time if inside.
That's also something you can do?
And then you can at the end just have one statement for the assignment of the states. So that might look better.
Maybe, yeah.
So one more question about the performance of the compilation this time. So in this examples, you had only single visitor in the entire code, I assume. And how does it scale? So if you have multiple visits or multiple variants in single compilation unit, what is the source of this compilation time? Because if it is just an include to variant, then maybe it isn't as bad as you have shown in the slides.
I think it is actually relatively bad. So I also looked, don't have it in this table, but I also looked at just the cost of including the variant header, and it's much less than this number. It's more like 15, 20 milliseconds. So I don't think the includes are the problem. I could imagine that the optimization also plays a large part here, since this variant visitation is a lot of template stuff, and so probably generates a lot of function calls that the optimizer then has to squish back together. So I didn't actually try compiling a non-optimized build. This would maybe be interesting to see what the difference is then.
This would mean that also if you have the same variant multiple times visited in different functions, then possibly it could be...
a good point. Then it might be less bad, yeah.
Okay, thank you.
For sure, yeah. All right. I guess it's time for coffee.